Hello everyone, welcome again to EGN 3343. This is thermodynamics, and today we are going to continue to talk about the second law of thermodynamics that we introduced in the previous lecture, and we are going to introduce the concept of entropy, basically as an artifice of this law of thermodynamics to be able to quantify some of the things that take place in real processes as comparison to ideal or perfectly reversible processes. Okay, so today's lecture is going to be entirely fundamental. It's going to be very conceptual. We're not going to be solving any problems. We're basically going to be introducing more statements about the second law of thermodynamics. And as we do, we are going to define entropy as a property. And we're going to leave it at that, just a definition type of lecture. Now, we said that the second law of thermodynamics is composed of a series of corollaries and statements, such as the Kelvin-Planck statement and the Clausius corollaries and the Carnot statements and so on. And another corollary of the second law of thermo is the Clausius inequality. Now, the Clausius inequality states that if you integrate over an entire cycle, this is what this circle means over the integral. So if you go around an entire cycle and integrate the Q over the temperature, or the heat transfer over the temperature, that integral should be less or equal than 0. Okay, that means that it is either negative or 0 at best. Applied to a cycle where greater than 0 stands for when the process is irreversible, and equal to 0 stands when the process or the processes within the cycle happen to be reversible. So if all the processes within the cycle are reversible, then the integral over the cycle, the integral over the entire cycle, or the summation of all the heat transfers over the temperatures as the temperature changes in each one of these processes over the cycle, is equal to 0 if all the processes were to be reversible. Remember that an integration is nothing more than a summation over small steps. So if we can take every single one of the processes that composes a cycle and break them up into small steps, and we can actually quantify the amount of heat transfer that goes into or out of the system at each of these small steps within the cycle, within each of the processes, and divide that by the corresponding temperature of the system at that small step, the summation of all of those will end up being less than 0 if there are any irreversibilities present in any of the processes. Now, to understand this concept a little bit better, we are going to use the Carnot power cycle. The Carnot power cycle is basically an ideal or an idealized heat engine. It's a heat engine that is composed of 4 processes, or it's a cycle made up of 4 processes, and each one of these 4 processes is perfectly reversible, both internally and externally reversible. And not only that, these 4 processes are composed or organized in such a fashion that we have 2 adiabatic processes and 2 isothermal processes. The first process, the process from 1 to 2, is an adiabatic compression. So basically, the system is compressed with no heat transfer. Process from 2 to 3, the system is placed in contact with a hot temperature reservoir or a hot reservoir, so that there is a heat exchange into the system, QH, and there is an isothermal expansion in the process. After the isothermal expansion, the temperature of the system is kept at a temperature TH at all times during the process. After the expansion takes place, there's a further expansion, but that expansion is adiabatic. So there's an adiabatic expansion, insulated. There's no contact with another reservoir, and there is no heat exchange in or out of the system. And then there is an additional compression after the system has expanded completely. There's an isothermal compression in which the system is placed in contact with a cold temperature reservoir at temperature Tc, and therefore the system rejects heat to the surroundings. Now, the reason why we call this an idealized or academic type of heat engine is because there is no practical implementation of this particular heat engine. It's very difficult to come up with a practical application or practical implementation where we would have a heat engine made up of a piston cylinder device in which we will accomplish these 4 processes in a perfect cycle: an adiabatic compression, isothermal expansion, adiabatic expansion, and isothermal compression. Now, this system allows us to study the concept of the Clausius inequality, or allows us to very easily implement the Clausius inequality and analyze where does it take us to. Now, if we look at the four processes in a Carnot power cycle, we have an adiabatic process from 1 to 2, an isothermal process from 2 to 3, an adiabatic process from 3 to 4, and an isothermal process from 4 to 1. So now let's take that integral of Clausius, the integral of dq over t, the integral of the heat transfer divided by temperature, and apply it to each one of these four processes. Okay? Now, let me do this from the start. The process from 1 to 2 is an adiabatic process, and therefore the integral from 1 to 2 of dq over t is equal to 0 because q is equal to 0. The process from 2 to 3 is isothermal. It's an isothermal expansion where the system is placed in contact with a reservoir at a temperature Th. And at that point, because Th is equal to a constant, the temperature of the system doesn't change during that process, we can take it out of the integral. So this integral is simply equal to QH over TH. The process from 3 to 4 is also an adiabatic process, so the integral from dq over t is equal to 0, basically because q is equal to 0. And the process from 4 to 1, which is a compression, is an isothermal compression when the system is placed in contact with a cold temperature reservoir and the system is kept at a constant temperature. The temperature in that integral comes out of the integral, and that leads to qc over tc. So the integral around the full circle, around the full cycle, the summation of all these four integrals is equal to 0 plus qh over th plus 0 plus qc over tc. Okay, so let me continue this. So the Clausius inequality, if all the processes were to be reversible, if all the processes in the cycle of the Carnot power cycle were to be reversible, the Clausius inequality states that the sum of all these integrals is equal to 0. So 0 plus qh over th plus 0 plus qc over tc is equal to 0, where qh over th remains the same, and since qc is heat rejected from the system, we know it's going to be negative, so we're going to force that negative sign. We're basically going to call it positive. We're going to place a negative sign right in front of it, and that's equal to 0 for a perfectly reversible Carnot engine. Okay, now if QH over TH minus QC over TC is equal to 0, we can conclude that TC over TH is equal to QC over QH. And that's where the Carnot efficiency comes from. Remember that the Carnot efficiency came from the fact or the assumption that the ratio of QC over QH would be equal to TC over TH according to the Clausius inequality. Now we can demonstrate directly that for a reversible Carnot engine, QC over QH is equal to TC over TH. So, if any of the processes within a Carnot engine were irreversible, or there would be irreversibilities within any of the processes in the Carnot engine, this ratio, TC over TH, will actually be less than QC over QH. And that comes directly out of the Clausius inequality, because for irreversible processes, or for an irreversible cycle, the integral over the cycle of dq over t is less than 0, according to Clausius inequality. And therefore, QH over TH minus QC over TC is less than 0. Solving for the ratio TC over TH, we can send this to the right-hand side and then have TC come multiplying to the left-hand side and QH dividing to the other side. TC over TH, the ratio of the thermal reservoir, the temperatures of the thermal reservoir is less than the ratio of the heat exchanged by these two thermal reservoirs. Okay, so the conclusion is, basically, knowing that the efficiency of a power cycle is equal to 1 minus Q out divided by Qn, which in this case is QC divided by QH, if this were to be applied to a reversible Carnot cycle, we know that QC over QH is equal to TC over TH, and therefore the efficiency of a reversible Carnot cycle is equal to 1 minus TC over TH. However, when there are irreversibilities in this Carnot cycle, the ratio TC over TH is always less than the ratio of QC over QH, and therefore yielding an efficiency that is less than the Carnot efficiency. That's why we can always conclude that the Carnot efficiency is the maximum possible efficiency that can be achieved in a heat engine. The efficiency 1 minus TC over TH is always the maximum possible efficiency achievable in a heat engine. And now we actually put numbers to this. We actually demonstrated it. Because of that ratio, because the ability of thermal reservoirs of exchanging heat, in the case of perfectly reversible ideal cycles, the ratio of the temperatures is equal to the ratio of the Qs. But In non-ideal cycles, the ratio of the temperatures is less than the ratio of the Qs. And if that's the case, then since QC over QH is greater than TC over TH, that yields an efficiency that is always less than the efficiency of Carnot. Okay, so this is just basically a conclusion that in the demonstration that the reversible Carnot cycle yields the maximum possible efficiency, maximum or larger than a real cycle. All right, so going back to the Clausius inequality, we say that the integral over an entire cycle, or the summation of all the heat transfers divided by all the temperatures of the system within a power cycle, is always less than zero, or equal at best. Now, in order to eliminate the inequality, we create an equation. And in order to create an equation, we introduce a quantity on the right-hand side. Instead of saying that this is less or equal than zero, we just say it's equal to some quantity, some parameter. And that parameter, we basically force it to be positive, and we stick a minus sign right. So this parameter sigma is always going to be a positive number, and the negative sign will ensure that this integral will always be less than zero, and at best will be equal to zero when sigma is equal to zero. So to create an equation from the Clausius inequality, we can write it in this form. We eliminate the zero on the right hand side, we eliminate the inequality sign, we turn it into an equality, and we call the right hand side sigma. This is just a mathematical trick. Now, the parameter sigma may be considered a measure of the strength of the irreversibility, or just simply the irreversibility. We're trying to measure the irreversibilities that occur in the cycle that make this integral be less than zero. We know that if the cycle is perfectly reversible, the integral will be equal to zero. But if the cycle is, or processes within the cycle are irreversible, then the integral will be less than zero. It will be less than zero by a quantity sigma. So with sigma, what we're trying to do is measure the strength of that irreversibility. So the characteristics of the irreversibilities are as follows. If sigma of the cycle is equal to zero, there are no irreversibilities present within the system. The system is perfectly reversible, or the processes that take the system from state 1 to 2 to 3 to 4 back to 1 are perfectly reversible. If sigma of the cycle is greater than zero, there are irreversibilities present. Remember that we just turn the Clausius inequality into an equality and make the right-hand side equal to minus sigma. So if sigma is greater than zero, then the integral is equal to a negative number, and therefore is less than zero. So there are irreversibilities in the system, and the more irreversible is the system, or the more irreversible are the processes within the system, the larger sigma is going to be. But sigma is always going to be a positive number. And the last conclusion is that sigma cannot be less than zero, because Clausius inequality says that that integral must always be less than zero. And therefore, if we equate it to minus sigma, sigma can never be a negative number, because negative times negative will yield positive, so we'll violate the Clausius inequality. All right, so now let's try to pinpoint these values sigma, but instead of trying to pinpoint the strength of irreversibility over the entire cycle, let's try to pinpoint it process by process. And in order to do this, let's just think of a cycle that is only composed of two processes. So let's think of a cycle that goes from state 1 to state 2 and back to state 1. It is a cycle because it goes back to the original state. But let's imagine that it does so in two processes. Process 1, 2, process 2, 1. Okay, so it's a two-process cycle. And we're going to think about a couple different paths to get us there. We're gonna imagine that the first cycle goes from 1 to 2 through path number A, and then it returns from 2 to 1 through path C. And there's another cycle, similar to the other one, that will take us from state number 1 to state number 2 through path B, and then it's going to return from 2 to 1, again through path C. So there's two cycles. One goes from 1 to 2 in a path A, and the other one goes from state 1 to 2 on a path B, and then they both return to state number 1 on the same path C. And let's assume that these cycles are perfectly reversible. Both of these cycles are reversible. Now, according to this, let's look at the cycle that goes from 1 to 2 through A and returns to 1 through C. The Clausius inequality states that the integral from 1 to 2 through path A plus the integral from 2 to 1 through path C, that's a return, is equal to the strength of irreversibility, which is 0, because we're saying that this is a perfectly reversible process. And now let's say that we are going to go from state 1 to state 2 on path B, and then we're going to return from 2 to 1 on path C as well, and we're going to say that those two paths are perfectly reversible. So the strength of irreversibility is 0. So integral from 1 to 2 through B plus integral from 2 to 1 through C is equal to 0, and integral from 1 to 2 through A and integral from 2 to 1 through C is also equal to 0. Now here we notice that this second integral on both equations are equal to each other. So all we have to do is subtract these two equations. If we subtract these two equations, this one minus this one will cancel out because it's the same integral going through C. So the conclusion is, let's go back, if we subtract these first equation minus this second equation, this integral over path C will go away because it's exactly the same integral over the same exact path. Okay? It is basically going from 2 to 1 on path C. And then by subtracting the 2, what we can say is that the integral from 1 to 2 dq over t on path B minus the integral from 1 to 2 dq dt over t on path A is equal to 0 minus 0, which is equal to 0. And the conclusion of that is that basically this one must be equal to this one. For these two things to be true at the same time, the integral through path B must be equal to the integral through path A. And that is the conclusion. If we compare the two equations, we can easily conclude that the integral from 1 to 2, from state 1 to state 2, which are the same, state 1 and 2, through a path A is equal to the integral from 1 to 2 through a path B, as long as the two processes A and B are reversible. As long as the two paths are reversible paths. So the conclusion is, since both path A and path B are arbitrary, just any shape that will take us from 1 to 2, except for the fact that both are internally reversible, both path A and path B are internally reversible, the integral of dq over t has to be the same for internally reversible path from 1 to 2. So basically, the integral of dq over t is path independent as long as the path is internally reversible. And therefore, that follows the characteristics of a property. Remember, way back at the beginning of the semester when we talked about what a property is, properties are quantities that are assigned a numerical value that define the characteristics or the state of a thermodynamic system. Well, in that regards, we define temperature as a property, we define pressure as a property, we define volume as a property. Later on, we define energy as a property, enthalpy as a property. So in following that particular definition per property, we can also conclude that the integral of dq dt, or dq over t, is also a property, because it's independent of the path. One of the main characteristics of a property is that it defines the current state of a thermodynamic system without regards of what the past state was. It needs no history. It needs no information from the history of the state or the history of the system. It doesn't care what the system was, what kind of properties it had an hour ago. It is just interested in the properties that it currently has. Okay? So this integral, therefore, follows the same definition. This integral is basically telling us that regardless of how we go from A to B, from 1 to 2, either we go from on a path A, on a path B, on a path W, it really doesn't matter. We'll always get to the same point, and that integral will be the same. Therefore, that integral has to be a property. There's a property that could be defined as the integral of dq over t. And that integral we basically call entropy, and we give it the name S. And S, entropy, is basically a strength of the irreversibility of a process. We said that this integral is equal to this change in entropy only for internally reversible processes, but we're not confining that to externally reversible processes. Okay? We know that processes might be completely reversible or just simply internally reversible. That means that processes could be irreversible, but there might be some irreversibilities, and what we do is just simply limit those irreversibilities to the boundaries. Internally, we keep them reversible. And that is the case for this definition. The integral from 1 to 2, from a state 1 to state 2 of dq over t is equal to the change in entropy between state 2 and state 1, or from state 1 to state 2, S2 minus S1. Okay? That can be done in absolute form, S2 minus S1, is integral of dq over t, and look at the units. Q is in kilojoules, is energy in the form of heat, and temperature is in Kelvin. So the units of entropy are kilojoules over Kelvin. Or it can also be done in specific form if we use the specific form of the heat, delta lowercase q, where the units of specific heat are kilojoules over kilogram. So the units of entropy or specific entropy are kilojoules over kilogram Kelvin, because of the temperature in the denominator. So this is how we define entropy, and now we're defining entropy as the characteristic or a property of a state at an individual state, and it can change from state 1 to state 2, and it's defined as this integral. So the entropy is just another property now, another property that we use to define the system. Before, we knew temperature, pressure, volume, energy, and entropy, and now we're adding entropy to that list, another property that we call S. Now this property has many repercussions and many interpretations. The first one is that it measures the strength of the irreversibilities that occur from state 1 to state 2. Okay? Now we're saying that this property is only defined this way for internally irreversible processes, but I also said that there could be irreversibilities, but those irreversibilities are confined to the boundaries. Those irreversibilities can now be measured through the entropy. The larger the entropy change, the larger the irreversibilities going through the boundaries are. Okay, so it measures the strength of the irreversibility of a process. It measures the ability of that process of doing work, or the efficiency or the effectiveness, better said, of a process in transforming energy from heat to work or from work to heat. Okay, now also we have some characteristics of entropy. According to the Clausius inequality, we can always say that, well, going from this definition, we can say that if we add Q, remember that T is always a positive value. Okay? It is in Kelvin, so T must be positive. Now, if T is positive, the value of the change of, or the sign of the change of entropy is related directly to the sign of Q. If Q is positive, that means going into the system, delta S is positive. If Q is negative, that means delta S is negative. If Q is equal to 0, then delta S is equal to 0. So if heat is added to the system, delta S increases, or entropy increases. Delta S is greater than 0. Entropy always increases when the system absorbs heat. If the system rejects heat, then the entropy goes down. The entropy of the system goes down. If the system is adiabatic, if the process is adiabatic, meaning the system is insulated, then there cannot be any entropy change. dq is equal to 0, and therefore entropy is equal to 0. But that is only true for adiabatic and reversible processes. If there are internal irreversibilities, then delta S is no longer 0. And what happens is that if you have an adiabatic process, but you have internal irreversibilities, the change of entropy will always be greater than 0, or basically the entropy will always increase. That's why entropy is always related to an increased value. There's no conservation. Nothing yields, nothing leads to a second law of thermo in terms of entropy. Entropy is just a mathematical artifact. It's a byproduct of these statements and corollaries that define the second law of thermodynamics that we use to actually quantify the strength of irreversibility of a system. If a system absorbs heat, the entropy goes up. If a system rejects heat, then the entropy goes down. If a system doesn't absorb or reject heat, the entropy doesn't change unless there are internal irreversibilities, in which case the entropy must go up. So if we have an adiabatic process, but within the process there are internal irreversibilities, the entropy can only go up. So it's great because now we have a property that would actually tell us the direction of the heat transfer, and not only that, it would also tell us whether there are internal irreversibilities or not. We can use it the other way around. If there are internal irreversibilities, we know that the entropy is going to go up as long as the process is adiabatic. If heat is rejected, the entropy is going to go down. Now, as I said, this entropy quantity or property has many repercussions and many implementations and interpretations. From the thermodynamic point of view, it's the strength of the irreversibilities that occur in the process. It's the a measure of the efficacy of a system to absorb or to actually transform energy from heat to work or from work to heat. And it also has interpretations and applications in other fields of science, like in cosmology, for example. We always say that entropy of the universe will always increase, and it does so because the universe is constantly expanding, and as it expands, the planets are getting farther apart, and as they're getting farther apart, the organization of the system of the universe is decreasing, or basically the disorganization of the universe is increasing. So as time progresses, the universe expands and the entropy of the system increases. The entropy of the universe increases because the universe is getting more and more disorganized. And as it gets more and more disorganized, it is more difficult for the universe or for elements within the universe to exchange energy with each other. When things are organized and tightly packed and compact, then it's easier for things to actually exchange and transform energy between each other. As things get more disorganized, it gets more difficult for things of this nature to occur. That's another interpretation of the second law of thermodynamics. It's another implementation of it. So let's ask a few questions. First of all, let's answer true or false. One of the corollaries of the second law of thermodynamics states that the change in entropy of a closed system must be greater than zero or equal to zero. Well, that's not true. This is false. Because there are cases in which the entropy of a system can decrease. And that is when the entropy, the system rejects heat. If the system rejects heat, if there's heat out of the system, the entropy will go down. So this corollary is false. The statement, when a net amount of energy is added by heat transfer to a closed system undergoing an internally reversible process, a net amount of work is also done. That is not true either. We can actually have energy going in the form of heat to a system in an internally reversible process, and the system, there might not be any work because the system doesn't change volume. Now, heat and work are related through the first law of thermodynamics through the change of energy. But now, in the second law of thermodynamics, the only thing that we relate is the heat. We relate the heat to the entropy. And what we say is, if there's a net amount of energy added to a system by heat transfer to a closed system undergoing an internally reversible process, we can conclude that the entropy will increase, not that work will be done. So this is false. A process that violates the second law of thermodynamics also violates the first law of thermodynamics. That's not true. That's also false. The first law of thermodynamics is completely independent from the second law of thermodynamics. One is conservation of energy, another one is a set of statements and corollary that define the limitations and the irreversibilities of a system. They are completely independent, but they both must be simultaneously verified in order for a system to be applicable, in order for a system to be real, to exist, to be plausible. So a process that violates the second law of thermo doesn't necessarily violate the first law of thermodynamics. The first law of thermodynamics states that the Q minus W is equal to change in energy. And that could be perfectly satisfied. But then we might violate the second law of thermodynamics. So one violating one doesn't mean that the other one is violated. But violating one means that the process is not plausible. A closed system can experience a decrease in entropy only when there's an energy transferred by heat from the system during the process. That is true. The only way to reduce the entropy of a system is by subtracting energy from it in the form of heat. The only way that the entropy of a system can actually be reduced is by it rejecting energy in the form of heat. By heat out, by rejection, by dumping energy out of the system. It has nothing to do with volume. It has nothing to do with making it more compact, smaller, compressing it, expanding it. It only has to do with heat. The only way for a closed system to experience or reduce or decrease in entropy is by rejecting heat. Entropy is produced in every actual process of a closed system. That is not necessarily true either. We know that entropy will be decreased if heat is rejected from the system. If there is no change in entropy between two states of a closed system, the process is necessarily adiabatic and reversible. Well, yes, that is true. and it works both ways. If a process is adiabatic and reversible, that means that the entropy will not change. If the entropy of a system doesn't change throughout a process, you can conclude that the process was adiabatic and reversible. Okay? So this is true. And G, the energy of an isolated system must remain constant, but the entropy can only decrease. An isolated system means Q is 0 and W is 0. An isolated system, remember, is a system that doesn't experience heat transfer or it doesn't experience work. Isolated, not insulated. Now in this case, we know if Q is 0 and W is 0, delta U is equal to 0. So the energy of a system remains constant. That's true. But the entropy cannot remain constant, cannot decrease. The entropy must increase or at best, remain constant. If the system is isolated, that means that Q is equal to 0. If you have an adiabatic process and reversible, delta S is equal to 0. If you have an adiabatic process and irreversible, then delta S is always greater than 0. The only way for entropy to decrease is by removing energy in the form of heat from the system, as if the system rejects heat. Okay, so remember these answers, remember these questions. Now, what happens when a process is internally irreversible? Remember that we classify processes into reversible. They're perfectly reversible, both in and out. Then there are irreversible processes, where there are some irreversibilities, and then there are internally reversible processes where we can actually confine those irreversibilities just to the boundaries, but internally we can say that within the system the process is reversible. Now there are processes that are both externally and internally irreversible. There are irreversibilities in the process no matter what. Now in that case we can say that the change in entropy from 1 to 2 is equal to the Clausius integral, the integral of dq over t, that's the entropy transfer, plus some amount of energy production. We always say that delta S is equal to the integral of dq dt, or dq over t, only for internally reversible processes. But when the process is irreversible, there's an amount sigma that is added to this. And that amount sigma is always positive. Okay? Remember we said that if a process is adiabatic and irreversible, delta S will be larger than 0. And it's larger than 0 by this quantity sigma of entropy production. This is in the case of a closed system. In the case of an open system, the balance is slightly different. In the case of an internally irreversible process, the entropy transfer is given by the Clausius integral, now in rate form, dq dot over t, plus the summation of the mass flow rate times the entropies at all the inlets, minus the summation of the mass flow rates times the entropies at all the outlets, these are specific entropies, plus the entropy generation within the system, that could be considered the entropy production within the control volume, it can be produced because of internal irreversibilities, is equal to the change of entropy of in the control volume as a function of time, the entropy accumulation or storage. This is the transient term. For a steady state process, the right hand side goes to 0. And basically what we're left with is with entropy transfer and entropy production or generation. So the balance of entropy for open system is identical. Now let's go back to fundamentals, and remember that today's lecture is all about fundamentals. We're basically looking at this definitions of more corollaries and statements of the second law of thermodynamics, and that leading to the definition of entropy. And as I said, entropy is just a definition. Entropy is just a mathematical quantity, a mathematical trick that we use to measure the strength of irreversibilities. Okay? Don't think that there is such a thing as entropy, something that is tangible, something that we can touch, something that we can measure. There's not an entropymometer. It doesn't exist. Entropy is just a mathematical trick that we use to measure the strength of irreversibilities that occur throughout a process in a system. To this end, let's go back to the first law of thermodynamics to derive the so-called TdS equations. TdS equations are going to be very important because they're going to actually lead to equations that we can use to measure the entropy. Now, the equation that we had before, entropy is the integral of dq over t, well, that's very nice, but it's very conceptual. We cannot use that equation to actually quantify entropy in a process. We cannot calculate the infinitesimal changes in Q, the delta Qs, and divide that by the temperature, and then integrate that in a process. It is very difficult to do in actuality, in reality. What we need are equations that we can use to relate entropy to other properties of the thermodynamic systems, like temperature, pressure, volume, and so on. And in order to do so, let's derive these TdS equations. So let's start from the first law of thermodynamics. The first law of thermodynamics states that the change in energy is equal to Q minus W. And we can actually do this in differential form. The change in energy, we're going to call it du, and Q, instead of having a finite amount of Q, we have a differential amount of Q. Delta Q minus delta W, a tiny piece of a process. Okay? So the change of energy in a tiny piece of a process is equal to the change in, or the heat transfer in that tiny space of the process minus the change of work in that time, or the work in that tiny space of the process. Remember that the work is equal to PdV. The differential work is equal to PdV because the work is the integral of PdV. So, and the heat transfer, according to the Clausius inequality, dq is equal to TdS. Remember that delta S is equal to the integral of dq over T. Likewise, we can say delta Q is equal to TdS, or Q is equal to the integral of TdS. So essentially, the heat transfer is the integral of TdS, or the area under the curve in the TS diagram. The same way we said that the work is equal to the area under the curve on a PV diagram, we can say that the heat transfer is the area under the curve on a TS diagram. Now what we're interested in is using these two expressions, PdV and TdS. So we're going to replace delta Q by TdS, and we're going to replace delta work by PdV. And we're going to plug that in there, and we're going to solve, and at the end, we're going to take TdS to the left-hand side and everything else on the right-hand side, and that leads to the so-called first TdS equation. So the first TdS equation says that TdS is equal to delta to du plus PdV. This equation right now doesn't mean anything. It's just a differential equation. Later on, we'll actually take that equation and try to solve it for specific cases, like for an ideal gas, or maybe for pure substances. So to pure substances, a change phase. So we're going to try to quantify the change of entropy based on changes in energy and based on changes in volume by trying to integrate this whole thing. So this is the first TdS equation. Furthermore, we can take, for example, the definition of enthalpy. Remember that enthalpy is equal to U plus PV. If we take the differential of these, then we can say that dH is equal to du plus the differential of PV, and then we can solve this by chain rule. So dH is equal to du plus PdV plus VdP. We just chain rule the differential on the second term, PV. The differential of PV is the first one times the differential of the second plus the second times the differential of the first. Chain rule. So if H is defined as U plus PV, this is just the definition of enthalpy, then the definition of the differential of enthalpy is the differential of energy plus PdV plus VdP. And taking this, remember that this term was the right-hand side of the first TdS equation. We can combine that with the first TdS equation to yield the second TdS equation. And the second TdS equation relates to enthalpy rather than energy. First TdS equation is TdS equals du plus VdP plus PdV. Second TdS equation says TdS is equal to dH minus VdP. And again, later on, we will use these TdS equations to come up with finite equations or algebraic equations to calculate the change of entropy based on changes in temperature, volume, pressure, and so on. Okay, so that is it for today. Today we basically went over a fundamental lecture, a lecture of definitions, in which we introduced further statements of the second law of thermodynamics, and then introduced the concept of entropy, the most important concept in thermodynamics, entropy. And it's just a mathematical trick to be able to quantify the irreversibilities that occur in a process. And in doing so, we can actually interpret more conclusions as to how a process occurs in thermodynamics and what are the differences between a real in an actual, a real and an ideal process, and how can we limit the changes in a real process. Okay, so thank you for your attention, and I'll see you next class. Goodbye.